Can magnets generate electricity? Can we cause electricity to flow using magnets somehow? This very question and this very experiment in the late 1800s revolutionized the world. A man named Michael Faraday is the one to really start asking these questions and figure out the relationship between electricity and magnetism. And we would not have the technology that we have today without him and his experimental work. This experiment is a little bit complicated, so see if you can follow along with me. We have over here a plastic tube covered with a coil of wire. And then connected to it with wire, we have another tube with another coil of wire. So what do we have here? Ultimately, all these wires are connected in a big circle. So we have a big closed loop of wire. Now remember, what is capable of flowing through this closed loop? What can we have whenever we have a closed loop of wire like this? We can have electricity, right? So imagine now that over here, through this coil of wire, we drop a very strong magnet. It's called a neodymium magnet. So we have a magnet that's moving through a coil of wire. In fact, we could cover up the top of this tube and shake it back and forth. So a magnet moving through a coil of wire. The wire is connected in a closed circuit over here to another set of coils. And we have a compass within this tube. We drop the magnet. What do you think we observe? We observe the compass needle being moved around, the compass needle being deflected. So think about this. What is the only thing that is capable of deflecting, of moving the needle of a compass? A magnet, right? So we know that over here on the right side of our system, with this setup, we have magnetism, a magnetic field affecting the compass needle. Well, what was capable of giving rise to a magnetic field way back in our third experiment? Electricity, right? Remember when we had flowing electricity, electricity flowing through this closed loop of wire, what happened to the compass needle? It got deflected, didn't it? So, what can we conclude is happening over here? We must have electricity flowing. So electricity is flowing, giving rise to a magnetic field affecting the compass. So the compass shows us that there's a magnetic field, and the only way that can happen is if there has been electricity over here. We don't have a magnet on this right side of the system, we just have wire. So there must be electricity flowing through the wire. We know that because the compass needle is being deflected, there's a magnetic field. We've already concluded in a previous experiment that flowing electricity can give rise to a magnetic field. So where is the electricity coming from? We don't have a battery. Well, what did we have on the left side of our system? What did we do to cause all of this? We dropped a magnet through a coil of wire, didn't we? So what can we conclude? We can conclude that a magnet moving through a coil of wire is capable of generating an electrical current. It's capable of causing electricity to flow. The magnet moving through the coil of wire causes electricity to flow through the wire over here, and we have evidence for that because we had a magnetic field being generated by the electricity. This compass needle deflected. That's exactly what we're seeing in this little simulation in a little bit of a simpler way. I have a coil of wire and I have a magnet. And attached to the coil of wire, I have a meter that's going to show me voltage. Voltage, we will define it in our next video, but basically it is a measurement of electrical energy. You can think about it like that. So right now the voltage is 0, but if I have a magnet moving through the coil of wire, I generate some voltage. Do you see the voltage needle moving? So I am capable of generating electricity, of causing electricity to flow by moving a magnet relative to a coil of wire. So we can say all of this. Electricity flowing through a circuit can give rise to magnetism. Magnets can give rise to electricity. So we have just concluded that electricity and magnetism are very closely related. They are phenomena that are really one and the same. So we can now refer to them as electromagnetism. Energy that's stored or utilized due to the flow and arrangement of electrons in a substance. So electricity and magnetism are related. They're two sides of the same coin. They are a united phenomena, and it's all due to something known as an electron. So if I'm going to explain to you how electricity and magnetism work, what causes them, how they are related, we have now got to go on and discuss what an electron is. Hopefully you've heard that word electron before. Um, Here's a quick crash course in basic chemistry. We will be discussing this in our next unit, Unit 3 of this course. But hopefully you know that every bit of matter is made of atoms. Atoms are the basic building block of matter. So here's a picture of a carbon atom. An atom, every atom, is composed itself of little tiny particles, other particles that we refer to as subatomic particles, electrons, protons, and neutrons. The protons and neutrons are held together in a central core of the atom that we call the nucleus, and the electrons are somewhere on the outside. So the electrons are on the outside of every atom. That's what an electron is. It's a tiny particle. It has a very, very small mass. It has, by definition, a negative electric charge. Protons are positive, electrons are negative. So by definition, electrons have a negative electric charge. They're capable of being transferred and flowing through certain substances like metals. This is why wire has got to be composed of metals like copper. And electrons have this really funky property known as spin. So look at these pictures here. These are diagrams, representations of electrons. Every electron we have discovered has one of two different spin states. It's either spinning up, which we refer to as plus 1/2, or it's spinning down, which we refer to as minus 1/2. So remember what I said about electricity and magnetism. They're united as one phenomenon, electromagnetism, energy that's stored or utilized due to the flow and or the arrangement of these electrons. So these electrons can have a flow. They can be flowing through substances like copper wire, or they can be arranged in a certain way. So let's talk about that. Here I'm going to define electricity as the unidirectional flow. That means the flow in one direction. Say maybe that this represents two different wires, and the blue spheres represent electrons. Here you can see the electrons are just kind of hanging out. They're flowing randomly. They're kind of jostling around a little bit. They don't agree with each other. They're not flowing in one direction. So we don't have electricity flowing through this wire. But as soon as we hook up wire to a power source and in a closed loop, we can cause the electrons to flow in one direction, and that is the definition of electrical energy. It is energy that can be utilized, that can be transformed into other types of energy, or transferred from one object to another. It's energy, and it comes from the flow of electrons through a substance. And again, only certain substances allow electrons to flow through, typically metals like copper. So if we can motivate these electrons to flow in one direction, by kind of giving them a little power source like a battery, we can cause the electrons to flow, and yes, they must be flowing in a closed loop. Remember, we've discussed this already. If we can get the electrons to flow in one direction through a closed loop, that is going to be useful energy for us. We can turn it into light energy. We can turn it into heat energy in your toaster. We can turn it into kinetic energy, like an electrical motor, etc., etc. Magnetism is due to the arrangement of the electrons. Some substances in nature naturally have electrons whose spins agree with each other. Most substances in nature have electrons whose spins disagree with each other. So that's what this little diagram is showing. In most substances, electrons are paired so that their spin states cancel out. So this electron is spinning up, plus 1/2. This one is spinning down, minus 1/2. And that results in no magnetic field. If, however, the electron spins are aligned, like in this substance here, wherever you see an arrow, that represents an electron, and we can see that all the electrons are aligned, that is going to generate an overall magnetic field. Why? Well, because the fact that electrons spin at all causes every single electron to behave like a tiny magnet. Electrons are magnets, basically. The spinning of an electron gives rise to this magnetic field. That's what these red lines indicate. Magnetic fields have a direction. You can see here, north and south, the magnetic field is kind of going up and out. Here, in the negative one half, the downward spin electron is the exact opposite. North is on the top, south is on the bottom. The field is kind of going down. So if you have electrons in a substance that are paired up with opposite spins, their spins are going to cancel each other out. You're not going to have a magnetic field. It's like the two fields are working against each other. They don't agree. There's no magnet there. The overall substance is not a magnet. Even though every individual electron does indeed behave like a magnet because of its spin, if you get electrons that are paired up with opposite spins, their fields will cancel out. You're not going to get an overall magnet. In order to have a magnet, the electron spins must be aligned. So magnetic fields arise due to the alignment of electron spins in a substance. Here, this substance, all electrons are spinning in the same way. They all agree with each other, so their magnetic fields would add up. They would add together to create a strong overall magnetic field. That is exactly what's happening in this picture here. The magnetic field is due to the fact that this substance, this bar magnet, has all of its electrons spinning in the same way. And all of those individual tiny little magnetic fields from every individual electron, because the electrons are spinning in the same way, their spins are aligned, their magnetic field agrees with each other. And so it creates this overall large magnetic field. So we can explain electricity and magnetism with the same underlying explanation. It's all due to the magical, wonderful electron. Either electrons flowing in a closed circuit in one direction around a closed circuit, allowing us to extract useful energy, or electron spins being aligned. And that gives rise to a magnetic field, which is almost like a type of potential energy, a potential to cause a change. I want to kind of contextualize all this for you and remind you of something we've already discussed as an energy diagram showing how electrical power is generated, how you get electricity in your home from an electric power plant. Ultimately, we said that every power plant, whether it's a hydroelectric dam or a nuclear power plant or wind energy, coal-powered, fossil fuel-powered power plants, they all generate electricity, and they all do that by spinning a turbine. So in this example, we have the coal as fuel, and it's burned to create heat. So that's thermal energy. And that thermal energy goes to boil water, and we have steam, very, very high energy, fast moving steam. So the hot, quickly moving steam is a form of kinetic energy, and it's used to spin a turbine. And then somehow magically, we discussed earlier, that spinning turbine generates electrical energy. Well, now I kind of want to show you how exactly that works. Here we have a turbine that is going to, because it has encountered this hot steam and it's been engineered correctly, it's going to spin very, very, very quickly. Well, remember what we said earlier. Whenever you have a coil of wire moving relative to some magnets, it's going to generate electricity. Remember, that's what we saw right here. A coil of wire, moving magnets, we're generating electricity. So how can we generate electricity using magnets and wire? We need kinetic energy. Really, the same principles we've been using are applying here. I'm taking kinetic energy and just transforming it into electrical energy. The kinetic energy of this magnet, because magnets and electricity are very closely related, they can give rise to each other. The kinetic energy of this magnet is giving rise to electrical energy, ultimately in this little picture being transformed into light energy. So it's just energy transformations. But now we know how it works. The kinetic energy of the hot steam turning the turbine generates electrical energy, because whenever we have a coil of wire and magnets moving relative to each other, electrical energy is generated, because magnets and electricity, magnetism and electricity, are so closely related. and they're caused by the same thing, by electrons.